In the archives of the United States government are maps that look less like civil engineering plans and more like preparations for nuclear war. Across the narrow land separating the Atlantic and Pacific Oceans, planners marked possible canal routes. But instead of fleets of excavators, some studies proposed lines of buried nuclear explosives. One estimate for a 48-mile route through Panama involved approximately 300 devices. The objective was not to destroy the Panama Canal. It was to create another one, a wider sea-level waterway without locks, excavated partly by nuclear explosions. If you want more stories of impossible industrial ambition from industrial empire, subscribe to the channel. It never received final construction approval and no nuclear device was detonated in Panama. But this was not merely a strange suggestion scribbled in the margin of a Cold War memo. Congress established a commission. Scientists performed nuclear excavation tests. Engineers investigated routes, calculated crater dimensions, and studied whether hundreds of explosions could cut an open channel between two oceans. For a brief period, the United States treated the Panama Canal as a serious engineering possibility. And the most surprising part is that the idea did not begin with nuclear weapons. It began with a genuine limitation inside one of the most important machines America had ever built. The Panama Canal appears on a map as a narrow blue line crossing Central America, but it is not a simple trench through which the Atlantic and Pacific flow directly into one another. Ships entering the canal are raised through locks to the level of Gatun Lake, carried across the interior of Panama, and then lowered through another series of locks to the opposite ocean. The system allowed engineers to avoid excavating one continuous channel all the way down to sea level. That decision made the original canal possible. It also placed permanent limits upon it. The lock chambers restricted the dimensions of ships that could pass. The gates, pumping systems, and water supply created critical points of failure. Every transit required an enormous quantity of fresh water, and a serious attack or mechanical breakdown at the correct location could disrupt the entire route. By the middle of the 20th century, ships were becoming larger. Military planners were also thinking about what one well-placed nuclear weapon could do to the locks. A sea-level canal, without the need to lift and lower every ship, appeared to offer greater capacity and fewer vulnerable mechanical components. The dream was older than the atomic age. Engineers had studied sea-level routes through Panama, Nicaragua, and Colombia long before anyone suggested using nuclear explosives. The obstacle was brutally simple: cost. The existing canal had required one of the largest excavation campaigns in history. A new sea-level route would have to be wider, deeper, and potentially much longer. Instead of using a lake to carry ships across elevated terrain, engineers would need to remove that terrain. Conventional excavation meant years of blasting, digging, hauling, and stabilizing hundreds of millions of tons of material. The route would cross mountains, rivers, rainforest, and unstable ground. Even if the United States could afford it, no one could guarantee that the final cost would resemble the original estimate. Then the nuclear age offered what appeared to be a shortcut. In 1957, the US Atomic Energy Commission established Project Plowshare, a program intended to find peaceful industrial uses for nuclear explosions. The name came from the biblical image of beating swords into plowshares. Nuclear weapons had been developed to destroy cities and military targets. Plowshares supporters believed the same energy could be redirected toward construction, mining, and energy production. A nuclear explosive buried at the correct depth would not produce the same effect as a weapon detonated in the air. Much of its energy would pass into the surrounding ground, crushing rock, creating an underground cavity, and forcing vast quantities of material upward. If buried too deeply, the explosion might remain contained and leave a collapsed underground chamber. If positioned closer to the surface, it could produce a crater. That raised an extraordinary possibility. If several devices were buried in a line and detonated in a carefully designed sequence, their craters might overlap to form a continuous cutting. Supporters imagined blasting harbours from coastlines, excavating passes through mountain ranges, creating underground storage chambers, and fracturing deep rock formations to release natural gas. Roads that would normally require years of drilling and blasting might be opened with a handful of detonations. And if the method worked on a truly colossal scale, perhaps it could dig a canal. Before Panama could become a nuclear construction site, however, the United States needed to prove that a nuclear weapon could function as an earth-moving machine. On the 6th of July 1962, a nuclear device was detonated beneath the Nevada desert in a test known as Sedan. Its explosive yield was approximately 104 kilotons, several times greater than the bomb dropped on Hiroshima. In an instant, it lifted a dome of earth above the desert, throwing soil and broken rock outward before the ground collapsed back into the enormous cavity. When the dust cleared, Sedan had created a crater approximately 1,280 feet across and 320 feet deep. Roughly 12 million tons of earth had been displaced. To Project Ploughshare's supporters, it was an astonishing demonstration. No fleet of conventional excavators could move that amount of material in a fraction of a second. The explosion appeared to prove that nuclear energy could perform useful physical work on a scale beyond ordinary machinery. But Sedan also demonstrated the central problem that would eventually destroy the entire concept. The material had not vanished. It had been pulverized, thrown into the air, and scattered around the crater. Along with ordinary soil and rock, the explosion released radioactive material into the atmosphere. The cloud rose thousands of feet and traveled far beyond the Nevada test site. Fallout was detected across parts of the United States. Sedan proved that nuclear excavation could move the ground. It also proved that the ground could become part of the weapon. Scientists continued experimenting. In 1968, Project Buggy tested the principle required for a canal. 5 nuclear devices were buried in a straight line and detonated almost simultaneously. Their craters overlapped, producing a trench approximately 900 feet long. The experiment demonstrated that a row of explosions could create something resembling a channel rather than a collection of isolated holes. But Buggy was still tiny compared with an interoceanic canal. Its 5 devices produced a trench measured in hundreds of feet. A canal across Central America would extend for dozens of miles, descend through elevated terrain, and require a navigable width and depth along its entire route. Scaling the idea up did not simply mean adding more bombs. Each section of the canal would behave differently. A device buried in wet sediment would not produce the same crater as one placed in hard rock. A charge beneath a mountain would need a different yield and depth from one excavating lower terrain. Detonations would have to be arranged so their craters connected without leaving barriers, unstable ridges, or sections too shallow for ships. The explosive sequence would also need to prevent one blast from damaging the emplacement holes or equipment prepared for later detonations. This was no longer one spectacular nuclear test. It was an entire construction system in which hundreds of nuclear explosions had to produce a continuous engineered landscape. In 1964, Congress created the Atlantic-Pacific Interoceanic Canal Study Commission. Its task was to determine whether another sea-level canal should be built, where it should go, and how it might be excavated. The Commission investigated conventional and nuclear methods across several possible routes. Some routes remained close to the existing Panama Canal. Others crossed the Darien region of eastern Panama or continued into Colombia. Engineers compared distance, elevation, geology, population, rainfall, political conditions, and the amount of material that would have to be removed. One Panamanian concept, usually associated with the Sassadi-Morty route, stretched for roughly 48 miles. Estimates suggested that nuclear excavation along this corridor could require approximately 300 explosive devices. The number made the proposal sound fantastical, but it emerged from a recognizable engineering calculation. Every hill represented material that had to be removed. For a conventional canal, engineers could calculate the number of excavators, trucks, drills, workers, and years required. For a nuclear canal, they attempted to translate the same landscape into explosive yields, burial depths, and crater dimensions. Lower sections might be handled conventionally or with smaller devices. Higher sections through the continental divide would demand far greater excavation. The resulting waterway had to be broad enough for ships and stable enough to avoid collapsing into itself. The proposed devices were officially described as peaceful nuclear explosives. Technically, that described their intended use. Physically, they would still produce blast, heat, radiation, ground shock, and radioactive debris. A canal created by 300 nuclear explosions would not necessarily require all 300 to detonate at once. Construction could be divided into sections and stages, but that introduced its own problems. After the first group of explosions, the surrounding terrain would be damaged and contaminated. Crews would still need to enter the area to inspect the result, drill additional emplacement holes, install equipment, and prepare the next section. If the crater dimensions differed from predictions, later charges might have to be redesigned. If a slope began moving, the project could not simply pause while thousands of tons of fractured radioactive material waited above the unfinished canal. And even if every explosion performed exactly as calculated, the resulting trench would not be ready for ships. A nuclear crater does not contain neatly finished walls. It produces broken rock, steep slopes, ejected material, and a raised rim around parts of the excavation. Conventional machines would still have to reshape sections, remove obstructions, and stabilize the banks. The canal would cross one of the wettest environments on Earth. Heavy tropical rainfall could wash loose material back into the cutting as quickly as crews removed it. Newly fractured slopes could absorb water, weaken, and collapse. This was especially serious because the original Panama Canal had already shown how difficult the region's geology could be. During its construction, enormous landslides repeatedly filled parts of the Culebra Cut. Excavation removed support from the slopes, rain entered weak layers, and hillsides moved toward the channel. Workers would clear the material only for more ground to slide behind it. Nuclear explosions would not eliminate that problem. They could magnify it by breaking rock well beyond the intended canal walls. Then came groundwater. A line of underground explosions could fracture aquifers, redirect streams, and connect previously separated layers of rock. Radioactive material might enter water systems and move far beyond the visible crater. Planners would have to determine not only where the canal water would flow, but where contaminated groundwater might emerge years later. The connection between two oceans created another layer of uncertainty. The Atlantic and Pacific sides of the isthmus do not maintain identical tidal conditions. A sea-level waterway could experience strong currents as water moved between them. Saltwater intrusion, sediment transport, and erosion would all have to be controlled. A nuclear explosion could create a hole, but it could not install navigation systems, stabilize every bank, manage currents, or guarantee that a tropical mountainside would remain where engineers placed it. The original promise had been simplicity, replace years of excavation with seconds of nuclear energy. The closer planners examined the complete canal. The smaller that advantage became. The explosions performed only the most dramatic stage. Almost everything required to transform their craters into reliable infrastructure remained conventional. Yet none of those difficulties was as politically dangerous as fallout. Nuclear cratering depended upon ejecting material into the open air. If the explosion were completely contained underground, it would not excavate the canal. The process worked only when earth and rock were thrown upward and outward. That meant radioactive debris was not an accidental side effect that could necessarily be engineered away. It was closely connected to how the excavation occurred. Supporters hoped that specially designed devices could reduce the amount of long-lived radioactive material. They also studied weather patterns, attempting to identify conditions that would carry fallout away from populated areas. But a project using hundreds of explosions could not depend upon perfect winds hundreds of times. A change in weather could send contamination toward towns, neighbouring countries, shipping routes, or the Caribbean. Rain could pull radioactive particles from the atmosphere and deposit them far from the canal. The proposed route was not an empty testing ground owned by the Atomic Energy Commission. It crossed a sovereign country containing communities, forests, rivers, and wildlife. People would have to be evacuated not only from the excavation zone, but potentially from a much wider fallout region. Panama would be expected to accept the possibility that a foreign power might permanently contaminate part of its territory while creating a canal whose ownership and control were already politically contentious. Colombia, Costa Rica, and other countries could also be affected by fallout or altered water systems, even if no device were placed within their borders. Then there was the 1963 Partial Test Ban Treaty. The treaty prohibited nuclear explosions in the atmosphere, underwater, and in outer space. Underground explosions were permitted only if radioactive debris did not spread beyond the territorial limits of the country conducting the test. A nuclear canal presented an obvious conflict. The explosions were buried, but their purpose was to break the surface. Radioactive material would be deliberately vented as part of the excavation. The United States could not simply label the detonation's construction work and make their international consequences disappear. Project Plowshare's own experiments were also weakening confidence. Sudan had created an impressive crater, but it had also produced substantial fallout. Other tests intended to release natural gas from underground formations discovered that the resulting gas could contain unacceptable radioactive contamination. The program repeatedly demonstrated the same pattern. Nuclear explosions could produce the desired physical effect, fracturing rock, forming a cavity, or creating a crater, but the useful product could not always be separated from radioactive material. A harbour contaminated by its own construction was not useful. Natural gas that could not be safely sold was not useful. And a canal that distributed fallout across Central America could not be judged successful merely because water fitted inside it. Economics, which had created the nuclear proposal, now turned against it. Nuclear excavation was supposed to be dramatically cheaper than conventional digging. But early estimates struggled to include the full costs of evacuation, monitoring, compensation, decontamination, slope stabilization, conventional finishing work, and long-term environmental management. It was easy to calculate the price of a device and the amount of rock it might displace. It was far harder to calculate the value of land that might remain contaminated for generations. The canal also required further proof tests before anyone could begin construction. Engineers had not demonstrated the enormous yields and road charge arrangements needed for the deepest sections. Those tests would themselves produce fallout and face international opposition. The technology could not be approved without more experiments, but the experiments required to approve it were becoming politically unacceptable. By 1970, after years of investigation, the Atlantic Pacific Interoceanic Canal Study Commission delivered its conclusion. Nuclear excavation of a sea-level canal was not currently feasible. The Commission did not claim that nuclear energy lacked the power to move enough material. That had already been demonstrated, the technology failed because a canal was not simply a missing volume of earth. It was a permanent transportation system passing through unstable geology, moving water between oceans and operating alongside human communities. Creating the empty space was only the beginning. The Commission regarded a conventionally excavated sea-level canal near the existing Panama route as the more practical long-term possibility. Even that proposal faced immense costs, treaty negotiations, and political uncertainty, and it was never constructed. Project Plowshare continued investigating other uses for peaceful nuclear explosions, but no nuclear canal followed. The last American Plowshare detonation occurred in 1973. The program eventually disappeared after its proposed commercial applications repeatedly failed to overcome contamination, cost, and public opposition. The Panama Canal continued operating through its locks, rather than replace it with a radioactive sea-level trench. Panama eventually expanded the existing system using conventional engineering. New, larger locks opened in 2016, allowing many ships that were too large for the original chambers to pass. That solution was expensive and complicated. It required years of construction, immense quantities of concrete, and enormous new lock gates. But it did not require detonating 300 nuclear devices across the country. Today, the nuclear canal survives through declassified reports, route maps, and excavation studies. Those documents capture a moment when atomic power appeared capable of solving almost any engineering problem, as long as the problem was measured only in tons of material moved. Project Plowshare proved that nuclear explosions could transform a landscape in seconds. It also proved why speed is not the same as control. The proposed Panama Canal was abandoned not because it was physically impossible to blast holes across Panama, but because blasting holes was the easiest part. The difficult part was creating a canal that remained stable, navigable, politically acceptable and safe for everyone who had to live beside it. And there was no nuclear shortcut for that.